So, as always, let's start by solving today's quiz. Okay. So, the definition of the magnetic moment was very simple. It was the current carried by the loop times the area of the loop, right? And how did I determine the direction? The first question should be the direction. We had this right-hand rule, right? I take my right hand and I run it in the sense of the current. So my thumb points along the magnetic moment, right? So I know that the direction of the magnetic moment is along the z direction, or I can say mu is the magnitude of the mu vector times k hat. Let's find the magnitude of this vector. I is given, n is given. What's the area? Well, the area of the full loop, pi times r square. R was also given. Good. Part A was very simple. How about part B? If a magnetic field B0 J hat. So which way is the magnetic field pointing? It's in the y direction. So the magnetic field is essentially like this. Calculate the torque on the ring. What was the formula we derived for the torque? Torque was mu cross B. Okay. Now, mu is mu magnitude times k hat, and B is B0 times J hat. So, if I use the expression for mu magnitude, I have I and B0 pi r square k hat cross J hat. What's k hat cross J hat? Well, you may remember that it's I hat, or if you don't remember that, k hat is along the z direction, J hat is along the y direction. So k hat cross J hat is not I hat, it's minus I hat. Okay, be very careful. If it was J hat cross K hat, that would be I hat. So this is minus I hat direction. What does that mean? So that's my torque. Blue. So this is my torque direction. Mu cross B. Okay. What does that mean? What kind of rotation does that mean? Every time if I have torque, angular velocity, whatever, it's a rotational quantity that's shown as a vector, again I use my right hand rule. I take my right hand, align the thumb with the vector, and my fingers actually show the sense of rotation. So here, which way, what's the sense of rotation of this loop? It's going to rotate. I mean, if I'm looking from the positive x-axis, it will rotate clockwise. Right? That's the sense of rotation. So tau torque magnitude is apparently I and B0 pi r square. Question?
So can you please explain why is it rotating clockwise? How are you going to,
Okay. So first of all, anytime the way in physics 101 we associated vectors with rotational quantities. And the way we did that was to use the right hand rule. For any sense of rotation, my thumb shows the sense of the vector. So here my torque is along minus x-axis. So my rotation is clockwise if I'm looking at from the positive x-axis. Okay? Any questions? Good. Now, what have we done about magnetic field so far? We have talked about how magnetic field affects current, how it affects charged particles moving with velocity v, and finally how it affects if I have a current loop, right? However, we haven't discussed one very important property. How does one create those magnetic fields? And where do they come from? Right. So the next thing we should discuss is the sources of magnetic field. And actually, this is sort of a feedback process. I told you that magnetic fields create forces on moving charges, and the reverse is that magnetic fields are created by moving charges. What do I understand from moving charges? Well, maybe really individual particles moving in vacuum, but more importantly, instead of saying moving charges, maybe I should say they are created by currents. Okay. So the source of magnetic field is always a current. And initially, I think we have one student from Manisa here, right? So my friend from Manisa will object to that. He'll say, no, no, no. Okay, currents may be creating magnetic fields, but there are these wonderful stones from Manisa which apparently also create magnetic fields. So how about permanent magnets? Right? I told you that if I take a permanent magnet, there is a north pole and there is a south pole, and there is clearly some magnetic field created by this object. The magnetic field is something like this. Okay. So maybe should I actually add another item to my list? Should I say their magnetic field is created by currents and stones from Manisa? Not really, no. And for a very long time, it was very mysterious, because people actually tried to measure if there are any currents in these stones, right? So they tried to see if there is any voltage drop. Nothing like that. Thankfully, really only over the last century, it became clear that if I actually zoom in into this permanent magnet, I'll see pretty much regular arrangement of atoms. And what do we have inside each atom? Inside each atom, so I'm going to zoom again, and this is a cartoonish picture, I know, but there is a nucleus of positive charge, and there are electrons which are practically orbiting this nucleus. And is that a moving charge? Is that a current? Well, yes, that is a current. So what happens is that my electron orbiting my nucleus is pretty much like a current loop that we've discussed in the quiz, which means it must have a magnetic moment mu. Now, the calculation of that magnetic moment mu cannot be done using the methods we have learned in Physics 101. It's beyond classical mechanics. We need to know quantum mechanics. Actually, in my quantum mechanics lectures, just this week, we are calculating this magnetic moment of an electron in a hydrogen atom. But it sort of makes sense. Because the electron is moving, it's like a current, so it should create a magnetic dipole moment. Okay? So this is like a current. It creates a magnetic dipole moment. But now, you may be tempted to say, hey, if all atoms have electrons, all the electrons are moving, so why are not all materials magnetic? And the answer, there are two parts to that answer. One part is that because of quantum mechanics, sometimes this magnetic moment, the magnetic field created by a single atom, may be zero. More common answer is that generally when you make a solid out of these atoms, these magnetic moments are randomly aligned. So from one atom to the next, there is no correlation between the direction of these magnetic moments. So one atom is trying to create a magnetic field one way, the other is trying to create a magnetic field the other way. So when you average out over many atoms, what you get is just zero. Okay? So the average magnetic field created by an ordinary substance is zero. For some substances though, and it again depends on the quantum mechanical interactions between the atoms in a solid. Sometimes the magnetic moments, the currents in each atom like to align. It's energetically favorable for them to align. Right? So, for example, if I take iron, it turns out iron has all these nice orbital currents and also what's called a spin current. So in iron, and actually if you tell them once, if you tell the atoms to align once, they will remember that. Okay? So you can magnetize iron and you will actually create a nice magnetic field because of these atomic currents. All right? And what's really interesting, what's really strange is that these atomic currents are not dissipative currents. They do not actually, the electron just keeps going there. And because of the nicety of quantum mechanics, these are not like currents you run through a resistor. There is no heating due to these currents. But we can actually measure them. We can see how they run in a material. And the study of magnetism, the microscopic origin of magnetism, is very hard. Okay. It's actually so hard that we can predict a lot of things about materials, but it's very hard to predict whether a given material, let's say your chemist friend synthesized a new compound and she wants to know if that's going to be a very good magnet or not. Ordinarily my computer will be able to tell me if it's going to be a good conductor, if it's going to be a strong material, if its tensile strength will be large. But it's hard to predict how good of a magnet that's going to be. For a very long time, nickel and iron compounds were the best permanent magnets. In 1990s, really, so close, only 20 years ago or so, some people they were trying to synthesize different compounds. They used a rare earth element called neodymium. I'm not sure if I spelled it correctly. And that really gave wonderful magnets. Okay, wonderful. This new material caused the magnetic properties to be stronger by a factor of 10 almost. Okay, so now we have very cheap, very good permanent magnets. And you may say, hey, magnets are for toys or for refrigerators, right? To stick something onto the refrigerator. Why should I care about magnets? It turns out permanent magnets are actually extremely useful. They are useful in a lot of industrial applications. One simple application is electric motors. To have a good electric motor, if you have a permanent magnet, a strong permanent magnet, that actually makes your motor much more efficient. And one of the reasons why electric cars are going down in price, they are becoming affordable, is that now we have these neodymium permanent magnets. Right? But so that's not our biggest concern now. As I said, it's really hard to calculate these atomic currents, what kind of magnetic fields they'll create. So let's do something simpler. Let's try to find out. So this is hard. Let's just find the magnetic field created by current carrying wires. So that will be our next step. Now, so the idea is the following. If I have some current carrying wire, okay, I would like to calculate what kind of magnetic field it will create at some point in space. Okay. Now there are two ways, and this is pretty much like what we did for electric fields, right? We said if I have a charge distribution in space, what's the electric field created by this charge distribution? And we had two tools at our disposal. One was Coulomb's law. I could separate my charge distribution into small parts, write by Coulomb's law the electric field created by each one, and integrate over the charge distribution. What was the second one? The second one was the Gauss's law. Okay, I could take a surface and say flux is related to the total charge inside. Again, I have two similar laws at my disposal for magnetic fields. Okay, the first one will be, so I'll do the reverse now. I'll first state the law which looks pretty much like Gauss's law. Okay, so first definition is going to be Ampere's law. Okay, and it says the following. Let's say that I have some currents. Okay, some current carrying wires, I1, I2, I3, and I'm trying to plot something in 3 dimensions. So, and Ampere's law tells me the following. It says choose any loop in space. Take a loop, not a surface now, but a loop. So I'll choose a loop which encircles these currents, okay? And choose a sense of rotation along this loop. So if I actually, let me do this a little more nicely. Now, so maybe instead of this 3-dimensional drawing, let me take a cross section. What does it look like? I have one current I3 going in, another current coming out, which is I2, another current going in, which is I1, and I have the loop which is going around those currents. Now, here is Ampere's law. Ampere's law tells me if I integrate the magnetic field along this loop, so I start from one point, I go around doing the B dot dl integral. And to remind me that this is a closed loop, I'll put this very sexy circle onto my integral sign. This is proportional to the net current passing through. And there is a proportionality constant which is called mu0, which is kind of like epsilon 0 for magnetic systems. All right? So this will be our law, and we'll use it in a moment. Don't worry about it. But let me make one more thing clear. What is I in? I in is the total current passing through my loop, but there is a sense. My loop, this is called my Amperian loop, it has a sense. So there is a sense of rotation here. So the sense of the loop is coming out of the board. Right? So if a current is coming out of the board, it's positive. If it's going into the board, it's negative. All right? So what is I in this case? The sense of the loop, as I said, is coming out. So I in here for this loop, I2 is coming out, so it's positive. I1 and I3 are going in, so they are negative currents. Okay? So there is a sense of rotation. The loop. Yes?
Why are you saying that I1 and I3 are negative currents? Because of the direction?
Because of the direction, because they are opposite. I1 and I3 are going into the board, where the sense of the loop I've drawn is out of the board. That's why they are negative currents. Good question. Now this is all too abstract. Let's actually solve one concrete example. Okay? Let's calculate. An infinite wire which is infinitesimally thin is carrying a current I. Find the direction and the magnitude of the magnetic field created by this wire. What am I going to do? Let me use the symmetries of this system. All right? I'll say the following. I'll say that I need to choose an Amperian loop. And how am I going to choose it? I'm going to choose it so that it actually encircles my current wire at a constant radius r. Now, what was Ampere's law? It told me that integral B dot dl is mu 0 times I in. First of all, let's calculate I in. What is the total current passing through my loop? Well, whatever is being carried, right? The total amount of current carried by the wire is I. Is it in the correct sense? Is it being carried in the correct sense? Yes, my loop is going around the wire, and it's actually in the same direction as the current. So I in apparently is just I. How about this B dot dl? Now, all the points on my loop are equivalent by the virtue of rotational symmetry. Okay. Furthermore, I know that this system is infinite, so there is no choice between up or down. So my magnetic field must be in the same plane as my loop. So I'll do the following. I'll say that on the loop, B is parallel to the L. Furthermore, because B and DL are parallel, magnetic field can be taken outside the integral by symmetry. So this is going to give me mu0 times I. What's the integral dl over this loop? It's the total circumference of my, or total length of my loop. So the length of my loop is 2 pi times r. So here, apparently, the magnitude of my magnetic field as a function of r is mu0 over 2 pi I over r. How about the direction? The direction is as follows. I've already said that the magnetic field is parallel to dl. So if I look at the system from the top, if the current is coming towards me, the magnetic field is basically encircling it in the positive sense. If I get closer to the current, my magnetic field will be larger. If I go away from the magnetic field, if I go away from the wire, my magnetic field will be smaller in magnitude. Okay. So this is how a single wire creates a magnetic field. All right? So this is Ampere's law. And unfortunately, you see, it relates global properties. To be able to use this, we need to know about the general structure of my current distribution, because I need to use symmetry arguments to find magnetic field itself. Okay, magnetic field in this law appears under an integral sign. To be able to take it outside the integral, I need to use symmetry. What if I don't have an infinitely long wire, but I have some wire which is bent, right? In such cases, Ampere's law is not going to be useful. We need an analog of Coulomb's law, which will tell me what's the magnetic field created by a small section of my wire, small current distribution. Okay. And thankfully, that law was discovered even before Ampere's law. Let me state it. It's called Biot-Savart law. It's an alternative to Ampere's law. It actually contains exactly the same information, just like Coulomb's law and Gauss's law were equivalent. Here, Biot-Savart law and Ampere's law are going to be equivalent. But it tells me the following. If I have a general wire, okay, carrying a current, if I want to find the magnetic field created by a small section dl of this wire, what I need to do is, this is where I actually want to find the magnetic field, dB created by this small section. Here is the length vector from dl to r. The magnetic field created by this small section is mu 0 over 4 pi times I times dl cross r hat divided by r square. Yeah, it's not as clean as Coulomb's law, right? First of all, cross product is involved. So let's figure out what this guy is saying. dl cross r hat, right? What does that tell me? It tells me that this small section is creating a magnetic field at that point, but which way is that magnetic field pointing? Just directions, let's forget about the magnitude. It's pointing in dl cross r direction. Here is my dl. When I do the cross product with r, what do I find? Magnetic field created by this small section is into the page. So magnetic field is into the page. Furthermore, it's telling me one more thing. What was the magnitude of dl cross r? It's dl magnitude, r magnitude, sine of the angle between them. So this small section, it's going to create zero magnetic field on its line of sight, if you want. And it will create the most current in the direction perpendicular to it. But let's also be careful. What is this r hat? R hat is the unit vector. R hat was r vector divided by r magnitude. Okay. I also see one more thing here. It's decreasing with r square. This kind of makes sense. If I go very far away from this piece of current, I should get less and less magnetic field. It's proportional to the current. Well, that's what I expect. More current, more magnetic field. And the proportionality constant turns out to be mu 0, another constant which looks like epsilon 0. All right? Now, let me state, again, this is very abstract. Let me try to solve exactly the same problem I solved with Ampere's law using this Biot-Savart law. Then we can compare and contrast, okay? So the problem I'm going to solve is, again, an infinite thin wire carrying current I. Find the magnetic field at a distance r away from the wire. So how do I do this now? Let me put some axes here. I'll call this the y-axis and this guy the x-axis. To be able to use a differential law, I need to break up my current into small differential parts. So that's what I'll do. I'll take a small section that's x away and has a thickness dx. So its dl vector will be like this. So what is the small magnetic field created by this small section? I need to look at the r vector. What's the r vector in the Biot-Savart formula? It's from the current that's creating magnetic field to the point where magnetic field is observed. Okay. Good. So what is dB? I have all the constants, mu 0 I over 4 pi in front. Now I need to be careful. I have dl cross r hat divided by r square. dl cross r hat. dl cross r hat is dl magnitude r hat magnitude times the angle between them. If this angle is theta, it's going to be sine theta. What's the magnitude of r hat? 1, right? R hat is a unit vector. By definition, its magnitude is 1. What's the magnitude of dl vector? It's dx. So I need just dx sine theta. But here's the thing. Let me call this distance, I don't know, h. I'm going to call it r, but at the end of the day. All right. Now, let me call this distance h. So, can you tell me what sine theta is? Now, the angle here is pi minus theta, but sine pi minus theta, 180 minus theta is actually sine of the same angle. So it's going to be h divided by square root of h square plus x square, right? Good. So let's actually take our break now. When we come back, I'll review and finish solving this problem.